So shockwave analysis, as I said, was a very useful tool when it comes to understanding what's happening on traffic, understand traffic dynamics, etc. In this part of the lecture, I'm going to talk about cumulative plots, which is another powerful tool in traffic analysis. A cumulative plot is a graph of a function n that gives the cumulative number of vehicles, or actually any moving object. It doesn't have to be vehicles. It could be pedestrians, it could be bicycles, buses, ants, animals, birds. So anyways, n is a function that gives the cumulative number of vehicles to have passed an observer by time t, starting from an arbitrary initial count, let's say 0 at time t0. So the actual plot is actually a stepwise function. So let's say at time t1, we see a vehicle. So we move up. And the number of vehicles and the cumulative number of vehicles that we have seen, if we've counted, is actually remains 1 until at time 2 where we count another vehicle. So we'll see a jump in the cumulative plot, and then it remains 2 until we see the next vehicle. So if the next vehicle appears at time 3, then we'll have another integer jump, and this keeps going. So the actual cumulative plot is called a stepwise function. However, we can say that we can approximate this stepwise function with a continuous function. So if we just connect all these steps together, we can say this n tilde t is the approximate function. So is the approximate continuous function of the stepwise nt. And the reason we are interested in making that approximation with a continuous function rather than a stepwise function, because if we have a continuous function, it's easier to work with. It can have a form, it can have an equation, we can take its derivative mathematically, etc. So in this case, what would be the slope of the curve here? Can somebody help me? What would be the slope of the curve? So if I take derivative of n with respect to time, what would this give me? What is the slope of the cumulative plot? What does it represent? It actually represents a flow, right? Because the slope of the line, let's look at the instantaneous slope of the line. What is it actually? It is actually delta n over delta t, right? So delta n is the number of vehicles, the change in the number of vehicles. So imagine it used to be 4, it's now 5. So it's actually, let's say 5 minus 4 over whatever delta t. And imagine this delta t is 1 second. So in this case, q would be 1 vehicle over 1 second. So if the slope of this nt is large, the flow is large. If the slope is small, the flow is small. Cumulative plots have a large range of applications. So it can be used with time-space diagram. It has it can be used in time count analysis, where we have arrival curves and departure curves. So going back to the time and space diagram, if you remember, the time and space diagram is one of the most useful tools in traffic analysis, which when we have one trajectory, when we have each trajectory, we can actually follow every trajectory in a time and space diagram and calculate so many things about traffic, like do the shockwave analysis, calculate flow, speed, density, etc. Time count diagrams are actually equivalent to this cumulative plot that we're talking about, because this is time and this is count, right? Or that cumulative plot NT. So it's a cumulative count, right? This cumulative plot or time count diagram is most useful when it displays the cumulative curves of upstream and downstream of a bottleneck. So we can say, imagine I have a bottleneck here. My bottleneck could be either a lane drop on the freeway, or it could be a traffic signal, right? So if I count the number of vehicles downstream, imagine I'm standing here, and I have my friend counting the vehicles upstream. What do we see? If I want to plot that cumulative plots downstream and upstream of a signal, what would I see? So let's try to draw that here. So I have time, I have n. So let's first draw the downstream one. The downstream one is actually can be called departure, because they're departing the traffic signal, they're departing the bottleneck, right? So how does it look like? If the traffic light is green, this curve moves upward, and then as soon as the traffic light goes red, this curve actually becomes flat, right? And then it continues again, and then it becomes flat, and then it continues again. But what about the upstream? So this is the downstream curve. So this is the downstream curve representing departures. But the upstream curve, so this is upstream, and this is downstream. And the upstream curve, I actually keep counting the vehicles, right? So this was departure, and this is arrival. So when the traffic light is green, I would count probably the same number of vehicles in the downstream and upstream, right? So it would be almost the same as the departure curve. So the arrival curve goes up. Again, we can say it continues to go. If this is sufficiently upstream of the signal, so it doesn't get interrupted by the queue of the vehicle, this would be the arrival curve. So this would be the arrival curve. This would be the departure curve. And then this can be used to actually calculate a lot of things about this bottleneck, which I'm going to talk in a minute or two. So let's go over some of the definitions before we dive into more technical stuff. So let's just start by establishing a relationship between cumulative count and flow. As I said before, if we approximate this piecewise function with a continuous function called n tilde t, the slope of this continuous function is actually representing flow. So that's an important thing to bear in mind. So that if we take the derivative of n with respect to time, that would be my instantaneous flow at every time, right? So at any time, if I take the derivative of this n with respect to t, that would give me the instantaneous flow. And going back to that arrival departure curve, if I plot in a time count diagram, if I plot the cumulative plots of the arrival and departure, just like the example I had for the traffic signal, the one on top, if that is arrival, and the one on the bottom is the departure, can somebody tell me what would be the area between these two graphs? So the area between the arrival and departure curve, what does it actually represent? So if AT represents the arrival curves and DT represents the departure curve, the area between these two curves, let's first find out what is the unit of that area. So let's step back and let's think about the horizontal distance. So let me clean up this area. What is the horizontal distance between the arrival curve and the departure curve? what's the unit here? What is this? This is of nature of time, right? Well, what is the vertical distance? The vertical distance is of nature of counts. So that's the number of vehicles. So it would be number of vehicles multiple. So if I want to calculate the area would be, the unit would be vehicles multiplied by time. And that is something which we usually call total delay. So the area between the arrival and departure curves here represents the total delay for that specific bottleneck, whether it was a signal or a lane drop on a freeway or anything else, or in any queuing system. If you have an arrival curve and a departure curve, the area between them represents the total delay that the vehicles all together will experience. And then what would be the, again, going back to the vertical line here that I was talking about. So what does the vertical line actually represent? It says at any time t, I can actually plot this vertical line, right? At any time t, it would be, the vertical line would be arrival t minus dt, right? So that is basically the number of cars and the queue in that, the number of cars in the system at that specific time, whether it's a queue or a lineup behind the signal or anything, that would give me the total number of cars waiting to depart. So the vertical separation between the two curves represents the number of vehicles between the observers at any time t. The difference between input and output is actually the change in the accumulation. So again, look, for example, at time 0, in this case, AT minus DT is actually equal to 0. That means there's no vehicle waiting in the system trying to leave. But at any other time, so this capital Q that is used here can also be called accumulation. Or in other words, it's the number of cars in the system, right? So how many vehicles are accumulated in the system, for example, behind the traffic signal to leave. And as I said before, the horizontal difference is representing the time that it takes for this specific vehicle to leave. So this is time. So that is delay for a single vehicle. So remember, n was the cumulative number of cars, right? So at any, so if I want to get, for example, this is vehicle number 10, vehicle number 11. So for example, vehicle number 10, I want to see how long it has to wait before it leaves the system. If I calculate this horizontal distance, that would give me the waiting time for that specific vehicle to leave the system. And now if I sum this, if I take the integral between arrival and departure in this case, that would give me the total delay of all the vehicles in the system. That's why the unit is vehicles multiplied by time. So for example, in this system, it would be, for example, 100 vehicles minutes. And if I want to show this waiting time mathematically, the vertical one was QT was AT minus DT, right? While WN, the horizontal one for any specific N, so this was T, this is N, is actually, because we're looking at the horizontal line, it would be the inverse of this function minus inverse of AT. Again, this is just a mathematical representation of what we just said. So it's the horizontal difference between A and D. And again, as I said before, the area is the total delay. So if you want to mathematically represent that, we can write, you remember the area between two curves is actually the difference between the integrals, right? So if I want to get the area of this curve, it would be the area underneath A minus the area underneath D. So it would be the area underneath A from T0 to T1 dt minus the area underneath curve dt from T0 to T1. And if I want to, I can also write it like this, that it would be T0 to T1 AT minus dt dt. So this is basically saying this is a mathematical representation of the area between the two curves. So nothing too difficult about it. But if I take that area between the two curves and divide it by the total number of vehicles in the system, so that would be the total vehicles in the system here is from the time 0 to time t1, how many vehicles we observe in the system. So it would be from n0 to n1, whatever that n0 and n1 on is. So if I get that area between the two curves and divide it by the total number of vehicles in the system, that gives me something that we call average delay per vehicle. So the total area between the two curves gives me total delay. If I divide it by the number of vehicles in the system, n1 minus n0, it gives me the average delay per vehicle. There is, again, an interesting relationship between the time-space diagram. So Tx is the time-space diagram, right? And Tn, which is the time count diagram, where if we assume Nt is a function that assigns to each point in the time-space diagram the number of the last vehicle that have passed. So for example, again, look, this Nt, the definition of Nt here is a little bit tricky. So Nt is a function that gives me the number of the last vehicle that have passed at any point on the time-space diagram. So for example, if I just randomly draw a point, if I draw a point here, what would be the last vehicle, the number of the last vehicle that has passed at this point? It would be 3, right? Because vehicle number 3 is the last vehicle that has passed this point. If I draw a point here, Nt would give me 4, because this is vehicle number 4. So this is vehicle number 1, this is vehicle number 2, this is vehicle number 3, vehicle number 4, vehicle number 5, vehicle number 6. So if I plot a point here, function Nt gives me 6 here. That is the number of the vehicle, the number of the last vehicle that have passed this point. So that's Nt, okay? Again, that's very equivalent to that cumulative plot that we were talking about. So if I take this is the important part, everyone. If I take the derivative of that Nt as defined here, with respect to time, that gives me the flow. If I take the derivative of that n function that is defined here, with respect to location, with respect to distance, it will give me the density. So look, let's do it again on the time-space diagram. So if I take the derivative of this Nt over some location, some distance, remember how would we calculate density? If we wanted to calculate density using time-space diagram, we would say we specify a stretch of the road from x0 to x1, and we just count, and we draw a vertical line at any snapshot of time, and we would just count how many vehicles do we see. So in this case, it would be 1, 2, and 3 vehicles. So density here would be 3 vehicles over the length of the road. x0 minus x1, right? That would be the density. If I want to calculate flow at any specific location, I would draw a horizontal line, and I had to specify a time window. So let's call that t minus 1 to t1. And I would count how many vehicles actually cross this horizontal line. So it would be 1 vehicle, 2, 3, 4, 5, 6. So Q would be 6 vehicles over t1 minus t minus 1, or delta t, whatever that delta t is from here to here. So the easy way of getting the flow and density from the time-space diagram. So this is very similar to that. We're saying if we take the derivative of that n with respect to t, we get flow. If we take the derivative of n with respect to x, we get density. And again, that leads to the first macroscopic fundamental model of traffic that we're going to introduce to you, which is called LWR model. What I would suggest is, I think because we are running out of time, let's stop here.